Alright, so here is our introduction to linear programming. Now, we're going to mostly worry about the modeling aspect of it. We'll leave the solution to Sage most of the time, I think. And what is a linear program? Well, it's a particular mathematical model, and so typically we talk about it in a canonical form. So canonical form, a canon is sort of the base form or the accepted form and so forth. So it's the canonical form. And if we can write a problem, and I'll just write some things here with, suppose I want to maximize, typically we might use a z or something like that. So maximize z equals, 3x1 plus 2x2 plus 5x3, something like that. But notice this is linear, okay, so linear programming. The program part, it's not that you're coding when you make this model. It's, however, when they first started, they were certainly programming. I am not exactly sure on the reason for programming as the name there, linear programming, but nonetheless, if we have a model that we can say we want to maximize, say something that looks like that, but it's just a linear function in more than one variable, usually it's many variables, and then subject to constraints. So, if I tried to maximize this function just as it is, well, everything would head off to infinity. Right? Quite typically, it is subject to some sort of constraints, and in the canonical form, we might have something like, maybe 3x1 minus. I was going to write a 2, but we've got that 2 up there, so 7x2 plus 4x3. Maybe that needs to be less than or equal to 15. So now, just looking at this so far, actually, if I let x2 get as big as I want, not a problem. Because then I can also make x1 and x3 get big. Well, they don't even have to, but I could let x2 go off to infinity. That would certainly be less than 15, and so I can still, this thing would still have an infinite answer. But maybe x1 plus x2 plus x3 has to be less than or equal to 12. And so now, certainly x2 could never be any bigger than 12. So at this point, there would be some non-infinite maximum here. Now you say, well, why not use negative numbers? Yeah. Well, we're in canonical form, and so, and I'll just kind of stop it there with those types of constraints. But in canonical form, we have that our variables x1, x2, and x3 are all greater than or equal to 0. And so anything we can write like that is called a linear programming problem. And so more generally, what we say is we want to maximize, and we can minimize and so forth, and we'll look at that in more detail in other videos. But so we want to maximize our z, and generally speaking, we would have some constant c1 times x1 plus some c2 times x2 plus c3 times x3 up to some cn xn, and then subject to, and here we would tend to write a11 x1 plus a12 x2 plus a13 x3 plus dot 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 plus a1n xn has to be less than or equal to some b1, and we would do this on down to where we would have an am1 x1 plus am2 x2 plus am3 x3 plus dot 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 plus amn xn is less than or equal to bm, and then the x1 x2 up to xn need to be greater than or equal to 0. So we have that. Now if we use a summation notation, we could write that as maximize z equal the sum of j equal 1 to n of cj xj. Okay, so we have that, but then subject to, and so we'll have the sum j equals 1 to n of aij xj must be less than or equal to bi, and then we would write I equals 1 to m, and then xj is greater than or equal to 0 for j equal 1 to n. So with summations, it makes it much cleaner, and you can even go so far as to do something like matrix notation if you know matrices. So z equals c transpose x subject to ax is less than or equal to b, where a less than or equal to in a matrix vector situation like this means that each row of this that we make has a less than or equal to. And then similarly you would write something like x greater than or equal to 0. And probably you would put a line over it to say that's a vector of zeros. So, you know, we can get very compact notation with matrices. With summations, we get a pretty compact notation, and if we write it all out, it looks pretty big, but that's all we're doing. And, you know, so if we have anything that looks like this, or can be made to look like this here, that is a linear program. And so that's the model. What we'll do is we'll just look at lots of situations where we'll figure out how to write them in a form at least something like this. Again, we'll talk more about that in another video, but at least something like this. And then we'll use technology to solve it. Okay, so there's our intro to linear programming.